and the flow rate is given is 100 mole per second. And then we burn this with air, right? So this is the reactor, and we use air which is at 300 degrees Celsius, right? So this contains oxygen and nitrogen. So I'll write the flow rate. Oxygen flow rate is 600 mole per second, and nitrogen, which is inert, 2256 mole per second, right? So that material balance part, you can do it here. They will tell you that, okay, this is in excess this many percentage, so you calculate this and then you get N2, so you can get an air flow rate. And the product is given here already after material balance. It is, so you have a component and mole of flow rate, I'll write down here and dot directly. So that O2 remaining comes out is 100, it is in mole per second, and nitrogen as it is 2256, and the CO2 complete combustion, so you get 300, and H2O you will get, so this is vapor, this is gas, this is gas, this is gas, and water you'll get 400. So this all gas, huh? You can mention G. Okay, so this is the problem. The reaction is, you can write it down, right? You know that you have to balance the reaction always, huh? So that's up to you. So do this one first. This is not given in the exam, you have to do this. So balance it. So you have 3 carbon, so 3 carbon here. And then you can find hydrogen, so hydrogen 8 here, so 4 here. So oxygen is here on this side, 6 plus 4. 6 plus 4, so 10 here, so here 5. Right, so this already done material balance in that way. So you can see, no, here conversion is 100%. So 100 mole of C3H8 is reacted, and it gives you 300 mole of CO2, 400 mole of H2. Right, you can verify this, so make sure that you there is nothing wrong in the data in the book or wherever you are referring. Okay, now this is what combustion reaction. So for combustion reaction, we have the standard heat of combustion is available. Standard heat of combustion means combustion reaction, standard enthalpy of reaction. So here delta HR dot for C3H8 is given as minus 2220 kilojoule per mole, right? So here, whenever they give standard data, so you have to refer that what this value represent. So in most of the book references, this value represent 2220 kilojoule per mole of the substance reacted. It means, or per mole of the product produced, but in stoichiometric quantity. So if I say 2220 kilojoule, it means it is for 1 mole of C3H8 reacted, coefficient 1, or 5 mole of O2 reacted, or 3 mole of CO2 produced, or 4 mole of H2O produced. And you have to also make sure that this is in which phase. The reaction also, when they say delta HR, then this is also given that this is gas phase, this gas phase, this gas phase, and this liquid phase. So you remember the table we have seen in the textbook where they have clearly mentioned that when there is a combustion reaction, products are considered are CO2 and other products are in gas phase. Only water they have considered is in liquid phase. So in this case, this is the equation, this is the reaction we have. Right, so let's start. So your first thing is energy balance, material balance is done. Now we have the delta HR of this reaction, but we need to find out the value of delta H for what is happening here for this particular flow rate. So for that, what we need is the value of psi. So here psi is straightforward. You can take any one component. You know the formula, Ni out minus Ni in divided by nu I. So you can take any one component. You can take C3H8, which is reacting, or O2 or N2. N2 doesn't work, CO2 or H2O. So for example, if we take C3H8, so 100 enters, nothing leaves. There is nothing here. So 100 divided by 1. So minus 100 divided by minus 1, so 100. You can take any other component, you will get the same answer, right? So you have the value of psi, which we'll need in the calculation. In case some fractional conversion is given or some other data are given, so you will have say 90% conversion. So you know that out of 100 mole, 90 mole will react. So your product composition will be different, and you will have C3H8 in the product. So in that case, psi is 90 in this reaction. Okay, now we go for this simple one right now. Say you have 100% conversion. So now next thing you have to prepare is the table, like we discussed. So you have a table, horizontal line. So here and one vertical line, and we list all the components. So we have in the feed we have this one. So they have given, this is given. What is the condition here is given 25 degrees Celsius. 25 degrees Celsius. This is 300 degrees Celsius, and the product which are coming are at 1000 degrees Celsius. You can note this. Okay, so once you have done this much, now you have to prepare inlet outlet enthalpy table. So for that, make a list of all the components, and we'll take the list of components which are present in the reactor. I mean in each of the streams. So here C3H8 gas form. So all are in gas form. So I'm not writing G everywhere. We understand that there is no two phases here. All are here. Whatever produces gas, gas, gas. Here all gas, vapor. So we just write it down. The list of all components: O2, N2, then CO2, and last one H2. So this all are in gas form. Now, one more thing I suggest you to add in the enthalpy table. So you make a two separate column. One is in. First have a look so you can prepare accordingly. In and out. And for in and out, you make Ni. So N in flow rate. Second, you write temperature of each component in, and then H cap in, H cap in, and same thing for out. So you have N out each component, T out. This is easier to avoid any mistake. Write the temperature in this table, which they have not written in any other books. H cap out. Right. So this much data we need. Once you have this data, that's it. You will be able to do the calculation. So only part left is the determining all this data. So this we have Ni in and Ni out. So this is 100. This is 600. This is 2256. This is not there. You put dash. So we know it is not present. This is not present. And then 100. This C3H8 enters at 25 degrees Celsius. And this enters at 300. This enters at 300. And out we have this C3H8, nothing comes out, so dash. O2 comes out 100 mole. N2, nothing doesn't react, so 2256 as it is. And this is 300 mole per second, this is 400. Done. Now give the name first thing. You give the name that this is H1 cap, this is H2 cap, this is H3 cap. And then this one here, the temperature of all the components are same, 1000. So you note it down that this is 1000, 1000. So this will avoid any mistake. They will tell you that, okay, one product they removed, which is coming out after all at the end at 100 degrees Celsius. So you may have different product at different temperature. So next thing here, H3. Okay, now next H4, H5, H6, and H7. Right, now we have to choose. First thing is the reference state. So reference state you have to choose for each component. So you can keep it different, you can keep same. We know that after all we are interested, this is nothing but a delta H with respect to reference state. So here for convenience, we can choose one data which is available in the reference table. So you can see that, you remember that O2, N2, CO2, H2O, one table is available in which you have the data given. Okay, now only thing you have to take care here is that this all are gas form, vapor form, but in the reaction, the delta H of reaction, this is given in liquid form. So you have two options to do here. If you take H2O in a vapor phase as a reference, 25 degrees Celsius, 1 atmosphere, then this you have to modify, this delta HR you have to modify, this you have to recalculate this based on that calculation. It means we are assuming right now this delta HR is based on the H2O liquid. You want to take it delta H2O as a vapor phase, then we have to add enthalpy of evaporation in this delta HR, that additional calculation. So instead of that, I will take del H2O right now in liquid phase as a reference. And from that reference state, I will calculate this H2O, which is coming out at this condition. So that's easy calculation. No need to touch this right now. So we'll take C3H8, all the components. C3H8, you have to make a list. O2, N2, and CO2. Now you have to mention the state of each, that this is gas, 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 and gas form. Only water we are taking in liquid form. And all are at 25 degrees Celsius, 1 atmosphere. Fortunately, here they have not mentioned anything about pressure, because we are neglecting the effect of pressure. You know that, right? If the reaction is taking place in gas form, the effect of pressure on delta H is negligible. Delta H is effect of that pressure difference is negligible. So you can ignore that part for the moment. So we assume 1 atmospheric pressure operation. This all cases, all reaction happen at this 1 atmosphere. So now we have the reference point. So H1 cap equal to, so H1 cap means what you have to do is you have to write this one first, that H1 cap is the delta H cap for enthalpy change from reference state, that is C3H8 gas form, C3H8 gas form 25 degrees Celsius to reaction condition. So here in the reaction, what is the condition? So reaction condition is also same, C3H8 gas form 25 degrees Celsius. So there is no enthalpy change here. This is 0. That is why we are putting 0. You understood now. That you have H1 cap means each of the enthalpy, this is nothing but the enthalpy change from reference state we choose to the process condition. Similarly, H2 cap is equal to delta H cap for the process of, so what is this H2 cap? O2. So O2 gas form 25 degree. This is the reference state. Every time, first thing you write reference state. From reference state to the operating condition. So operating condition is this. So O2 gas form, write the phase also, 300 degrees Celsius. We are ignoring pressure right now. We are keeping 1 atmosphere. As long as everything in gas form, don't worry about the pressure. So this we have to calculate. So how to calculate this L delta H2? So equal to integration 25 to 300 Cp of O2 in gas form dt. Or we can also calculate using the enthalpy data. So if you know the enthalpy at this state, enthalpy at this state, so we can calculate. So enthalpy of O2 at 300 degrees Celsius, H cap, minus H cap of O2 at 25 degrees Celsius. This both are in gas form. So this in gas form, this gas form. So if you have this data, it's easier. If you do not have this data, sometimes the table, the data given is out of range, so you may not be able to read these values. So in that case, you have to rely on CP formula. So in that case, you can do the integration and you know the CP formula ABCD. That value you take it from the table, substitute here, make sure you use correct units which are given in the table. So let's see the table now. So we'll go back. Physical property. Right, so you have table where CP values are given. So here is the CP value. Right, so you have the formula and everything is given here, 1 and 2. So you can go and check where is the formula for oxygen, nitrogen, oxygen here. So for oxygen gas phase, this is the formula. This formula form is 1, A plus BT plus CT square plus DT cube. And the range of this equation validity range is 0 to 1500 degrees Celsius. Within that range, you will get the correct value. Otherwise, you will get the incorrect answer because it is derived. This ABCD value are derived based on this range. So you have one way to do this, right? So you know how to do this one. Next thing is use the enthalpy table. So enthalpy table, we have table B8. Right. So in this case, here you have O2. What we want is the enthalpy at two different conditions: enthalpy at 300, enthalpy at 25. So enthalpy at 300 is this one, 8.47, and enthalpy at 25, 0. So we know that this table is prepared based on this temperature. So all enthalpy at 0 is 25 degrees Celsius or 0. So you can ignore this every time when you are writing this. Our reference is also 25 degrees Celsius. We can ignore this. This is 0. So directly here you can write H2 cap is nothing but enthalpy of O2, which is given in that table at 300 degrees Celsius. So this is 8.47. Make sure you write the units correctly. Up to here, any doubt? Any question? No.
Sir, the table already
Yeah.
uses the same reference state as the VR, yeah? So we just copy from the table directly.
Yes, yes, yes. Table you use that B8. It's good enough. Okay. So N2, nitrogen, right? Third one. So 25 to 300. So again, what you have to read? Only 300 or CPDT. You are interested to that integration you like, you do that. Or I'll take the value from here, nitrogen 8.12. So 300 degrees Celsius, 8.12 kilojoule per mole. And then H4 cap, H4 cap, what is it? So I'm not going to write now this. You understood that this is from reference state to desired condition, operating condition. So H4 is O2. You read the component name, read the temperature. So O2 at 1000 from 25. So you can directly write the value from the table. So this all are at 1000. I'll read at once. O2, N2, CO2. This I cannot use it. I'll tell you why. So O2, N2, and CO2 at 1000 degrees Celsius. We can read this three value directly from here. So you can see this 1000 degree O2 is this 32.47, N2 is this 30.56, and CO2 is this 40.48.6. Right. So this three value you can note it down. 32.47, that is the H4, 32.47, and H5 is 30.56, 30.56, and H6 cap is 48.6. 48.6. Right. Now, okay, all values are kilojoule per mole. Okay, now last one, H7 cap. So now what is H7 cap? So H7 cap means delta H cap for the process from reference state to desired state. So reference state is H2O in liquid state, H2O. So for H2O in liquid state at 25 degrees Celsius to final condition in our case is H2O vapor phase at 1000 degrees Celsius. Done. So now the data you may not be able to get easily this one because these two phases are different. So you have to do the path we did for the phase change calculation. So we are assuming 1 atmospheric pressure here. The process is taking place. That is important. You should have that data. Otherwise, here the values will be, this delta H will be significantly different because there is a calculation of delta H in the process in this calculation. So the first thing is, this is liquid. So always the first step is bring this liquid from 25 degrees Celsius to boiling point. So Cp of H2O in liquid state. So first sensible heat change. plus convert this saturated liquid at 100 degrees Celsius to delta HV of water at 100 degrees Celsius, enthalpy of vaporization. And then bring that vapor, which is saturated vapor at 100 degrees Celsius, to desired temperature 1000 degrees Celsius. So Cp of water vapor phase from 100 to 1000. Okay, is this clear? So you
So
have,
won't that calculation take a lot of time?
yes, it will. So this one calculation, you should know how to do it. You will get some instruction soon, then you will know that how to do this. You know how to use calculator for this CPDT calculation. You know the formula we have already discussed, that it is A plus BT plus CT
Yes,
square plus
sir.
DT.
So for like the exam, if we're showing this
Mm.
formula, do we have to write all the values on the paper, or can we calculate it directly?
No, you can put it value direct. I mean, you can write the formula that you are using Cp of water, that you have to mention it this much, this part. And if you have not mentioned this equation, it means I understand that you don't know how to do it. You got the copy from somewhere. So I don't want, you have to write the steps, this step. After this step, this Cp calculation, using the formula, you get the value. That value you have to write it for this term. So I can verify that you have done correct up to correct decimal points. This value from table, this value, again you have to calculate. So I don't want you to write the
Okay, so we
entire
just have to
Cp
write that
formula. That's
part.
it. Huh? I don't want we write 7.86 into 10 raised to minus 3 plus this into 10 raised to minus 5, and that's not the purpose right now. The purpose is you understand that this enthalpy change calculation require 1, 2, 3 steps, and this is this one, and the value of this you calculate, put it here, plus or minus, put it here, plus or minus whatever the value, put it here, and then final step. So you have to calculate each H1 to H7, for
Okay, sir.
example, separately, right? Okay. So next, what is the next thing? So you got all the data, right? That's over. Only thing left is this one. This is per mole. So now we can calculate the delta H. So we have delta H calculation here, nothing but multiply by psi. We have done in the previous slides we have shown. And then make a summation of all this, you will get the total enthalpy change for this reaction. So what we did here is we bought all these things, right, with respect to enthalpy change with respect to 25 degrees Celsius reference state. And then all these things also enthalpy change from 25 degree. So we have delta H, delta H, delta H, and then inside reactor what happens, that delta H. So we calculate all these things and you will get answer. You can note down delta HR minus 1.26 into 10 raised to 5 kilojoule. Final value of delta H dot, you will get minus 1.26 into 10 raised to 5 kilojoule per second. So what I suggest is you do this one, so you get the idea that how to reach this value. The formula we have already discussed in the previous slides to calculate this
So for
delta H.
delta, the total delta H, you just add up each one, right?
No. Enthalpy change, no, here. So we did the enthalpy calculation of this. This the H1 cap, H2 cap, H3 cap. So again, we have to use the formula that, okay, the enthalpy of outlet stream, summation, let me write it down, N out into H out, H cap out. So this N dot. So this will give you outlet enthalpy minus summation of N dot in into H cap in. Done. And plus reaction part. So plus psi into delta HR. Now, okay, this clear? This we have written in the previous slides I gave you already. So this is there. Okay, this is one way where you need delta HR. If this value is not available, you cannot do anything. It's impossible. And you have to make sure that this delta HR, you use reference state correctly. This H2O liquid, you use that. Okay, now in case this delta HR not available, delta HR is not accessible, or you don't know what is the reaction at all. For example, you have only this data. You have this data. What is the temperature, pressure, and the flow rate, and the composition here. Flow rates are given and temperature is given. You don't have any other data. You don't know reaction. You don't know enthalpy of reaction. So for that purpose, there is another method, second method, which is based on a reference state, which is chosen as elements instead of components. So here, say by chance we got O2 N2, but other two are this one, C3H8, we have taken as a molecule, as a reference state, and this CO2 as a reference state. But we can choose now reference state as elements. It's basic elements. So when we choose basic elements, say basic element means carbon here. Carbon occurs naturally in carbon state, solid state. So we'll take C as a reference state. In the reference state, we'll take C as a reference. Oxygen occurs in naturally O2, so we'll take it O2, N2 as N2, and H2. We'll add hydrogen, we'll remain, keep it as a H2 as the reference state. So now we have reference conditions, reference components are carbon, solid state, hydrogen, oxygen, nitrogen, H2, O2, N2 in a gas phase at 25 degree 1 atmosphere. So we don't need anything else. Now how to do that calculation? The difference here is material balance, everything is same. Enthalpy table is same. This will remain same. This doesn't change. This will exactly same. Only thing from here onwards, we'll have different calculation, and this will be different calculation. So I write it down here. So reference state we choose is carbon, solid, O2 gas, N2 gas, and what left? H2 gas. That's it. Don't take any molecule here. Only elements which occurs naturally at 25 degrees Celsius, 1 atmosphere. When you do this, it will take care of enthalpy of reaction in the calculation. You don't need it, because now we start with the element. It's like element balance we did in the material balance part. So it's easier. You don't have to worry about other things in the reaction. You don't need reaction. It will take care of itself, that you are finding the enthalpy change of reactant from element to reactant condition, reactant formula, reactant molecule. And then we find enthalpy change from element condition, from elements to product molecule. So you have both delta H with respect to this reference, which is this one. And then we take difference of those, that two enthalpy. You will get the enthalpy change of the everything, which is already done, right? You understand that, okay, you have a C as a solid state, you have H2 as a gas phase. So this two things, if you mix together, you get C3H8 in correct form, and you will get this in gas phase. So what is this calculation here? From C and H2, you get C3H8 in correct formula, is nothing but delta HF at 25 degrees Celsius. And then what happens is, in the reaction, actually in the reactor, what happens? This get destructed. C3H8 will be destroyed. It will be converted into C and O2 and H2O. So what we are doing here is that in between that destruction happen, that reaction happen here, that we don't bother what happens. What we do is, we take this with respect to this elements, and the product which are produced here, product which are produced CO2, H2O, that also enthalpy we calculate with respect to elements, not with respect to the reaction, reactant and product, that part. So we take it this as a reference state and find its enthalpy. So now we have enthalpy of all the reactants and enthalpy of the product with respect to elements. And then we take difference of this minus this, will give the enthalpy change, including temperature change and reaction. So here calculation will be a little bit different. So number name are same. H1 cap is the enthalpy of C3H8 at inlet condition. So H1 cap at this one. So we know that this is with respect to this condition. So with respect to this is nothing but delta HF dot of C3H8. Plus, you have to take care of temperature part. By chance, in this case, C3H8 already at 25 degrees Celsius in the inlet condition. So there is no other change, sensible heat change. These two things you have to remember every time. Whenever you take element as a reference state, each enthalpy calculation will have two parts: enthalpy of formation and this one. Second, H2 cap. Now H2 cap, you have to, again, two parts: enthalpy of formation and a temperature change. So H2 cap is, I just go back and show you. H2 cap is O2 at 300 degrees Celsius. This thing you have to remember. So O2 at 300 degrees Celsius. So enthalpy of formation of O2, 0. Plus what we need, enthalpy change from 25 degrees Celsius reference state to 300 degrees Celsius. So that is same like we have done before. Here by chance O2 is a element also. So it's nothing but this is the delta H cap for O2 from 25 degree to 300 degrees, which is same as before. This doesn't change. This is element for element, it will not change. So you will get the same value. Before we did was what, H2 cap 8.47. So H2 cap will remain same. This is this one. By chance it is 8.47, same. Right. So for element, enthalpy of formation is 0. So this is 8.47. Similarly, H3 cap. H3 cap also same. It is N2, nitrogen. Nitrogen at 300 degrees Celsius. So enthalpy of formation 0 plus enthalpy change from 25 to 300. So you know the value, it remains same. H4 cap, what is H4? So H4 cap is, so again, H4 cap and H5 cap, both are O2 and N2. So those two things, enthalpy of formation is 0. Temperature change is from reference state, which is 25 here and 1000 here. So again, this is also 25 here, 2000. So H4 cap is same as before, H5 cap is same as before, no change. Now H6 cap is not an element. H6 cap is for CO2. So now we have to do two parts. So part one, delta HF dot of CO2 plus enthalpy change of CO2 from 25 degrees Celsius to 1000 degrees Celsius, Cp CO2 gas phase dt. You know that this is optional. Huh? This you can read enthalpy data from enthalpy table. So you can directly read the value of H cap at 1000 degree minus H cap at 25 degree. This we did before. So this value you have already. This doesn't change. Only this value you will get. You need to take it from the table. Is this clear? You understood this part? H6 cap.
So that minus 25, do we need it because the 1000 already
Yeah. So
uses
this is, I'm
25 as
writing.
the reference state
This
here?
is redundant, but I'm writing it to make sure that in case you have a table which is not at 25 degrees Celsius and still you want to use, here you have, for example, you have 65 here. You want to take it 65 degrees Celsius as a reference state. So make sure you don't forget this term, second term. You have to write that H cap at 65 degrees Celsius.
So
And in
any other temperature,
Yeah.
we use this type of formula.
Which one?
Any temperature that isn't like 25, that doesn't have the reference state in it, we
Yes.
use this type of formula, 1000 minus 25,
For example, right now the table is given at 25 degrees Celsius. But for example, you have to take you want to take this at a different temperature for some reason. Then make sure that you do delta H. Even though this is 0, you have to verify that this is 0. In our case, this is 0, right? Okay, H7 cap, what is it? H7 cap, last H2O. So here H2O 1000 degree vapor phase. So we will start delta H. This is again, you have to write the state here. This is gas phase, this is gas phase. So here delta HF dot cap molar cap per mole, and this is the this is for water vapor phase plus integration. So we know this is the vapor phase. So this is hypothetical data. This is not the actual one. So this standard condition. So we have 25 degrees Celsius now H2O vapor, 2000 degrees Celsius Cp vapor of water dt. So this is only part is difficult. Steam table, if you refer, you will not have steam enthalpy, when it's water enthalpy, water vapor enthalpy at 1000 degrees Celsius, not easy to get it. You will not have anywhere in the table because it is very high temperature. So those data you need a special table, which you don't have. So it's better to use CP formula here. You don't have option, right? In case you find it, you can use it. Otherwise, you can use this one. Okay, so this is from 25 to 1000 degrees Celsius. So that's it. And what left? Anything else? No, that's it. All 7 you got it. So that's it. Now, when you use this, remember elements as a reference state in this method, your formula for delta H calculation will be different. It will be simply delta H dot is equal to summation of n out, n dot out into H cap out minus summation of n in dot H cap in. There is no reaction here because it's already taken care by the elements and this enthalpy of formation. This one, this one, this one will take care of it. Yeah, you can see it here. This is formation, formation, formation. When you put it here, it becomes enthalpy of reaction. So these 2 methods are there. You can do it anyone you like. You can start with this elements, 25 degree 1 atmosphere. In our case, let's fix it. Use 25 degree because its table is available. And then use this formula. So you need to calculate all H values, H cap values, in which you have 2 parts, enthalpy of formation plus temperature, pressure, phase change, anything here. H2 cap, again, formation plus this, formation plus this. Okay, so depending on data, so you have enthalpy of reaction is already given here, you can use this method. If enthalpy of reaction is not given and you would like to calculate it, you want to go for this method, then you have to calculate delta HR. Okay, and that calculation you know how to do it using enthalpy of formation. So you can see that both methods are actually similar, only representation is different. Here you have to calculate delta HR and then use this method, or you take it element as a state, reference state, and do this 5, 7 calculation and then put it here. Make sure same answer. Your answer may vary a little bit because in the books they have done the calculation using some tools, some software. So your values may vary a little bit, but the order of value, for example, 10⁵, so it will remain in the order of 10⁵. Okay, this is again, this example is from reference book where I have added few things here which they have not discussed. One is this one, delta HF, how to write. Every time 2 terms will be there, and you understood that why we are doing this. Apart from this, in the chapter 9 in reference book, they have given other examples. So 9 example number you can note down, 9.5-1 energy balance, or you can have a 9.5-2. You can read all the solved examples. Make sure you don't worry about iterative part. When they say some iterative calculations is required, temperature is missing in this case. So in that case, your this formula here, for example, this 1000 degrees is missing, then your all the CP formula will have one temperature is missing. So it's iterative calculation, which we will not have in CPC exam. That you still have 5 more semesters left to do all these things in your other courses, in the project and iterative calculation. Right now, it's straightforward, this calculation, which gives you in one step, you should be able to get either delta H or something else is missing, you'll be able to calculate. Okay, so first thing, read all the solved example and understand how they have done it. And again, in this all cases, in material balance, energy balance examples, what we are doing is, in energy balances, we put the delta EK 0, delta EP 0. When the reaction is there, we ignore all this part. There are complications later when we do the process design principles course. Okay, few more points left. One about enthalpy of mixing. You have done in thermo. We'll again look at point of view of our case in tutorial today. And tomorrow I want to do one more topic on humidity. So there is one chart which is called humidity chart, which from where you can read the properties of air water mixture at the given temperature or some other condition. So you can find out how much is the water vapor in the air, how much is the saturation, percentage saturation, how much is the moisture content in air, what is the dew point, what is the dry bulb temperature, wet bulb temperature. So that one chart is there. I'll cover it tomorrow. That's it. So typically we covered almost everything in the course. If something is required again in the next semester or after, we will repeat some of these things in other courses.
Sir,
Yeah. Tell me, sure.
sir, can you share the conversion table in the classroom?
Conversion means
Sir, like all the units, like the pressure, temperature, everything, and how we convert from one unit into another. Can you share that in the classroom?
I shared already. It's there in the PPT unit in the classroom. You see the PPT.
Sir, sir, but I think some of the units are missing in that.
Uh, for pressure or which one? Which unit? You tell me now.
Yes, sir, pressure.
Pressure, no? Okay. So pressure, you can refer slides lecture 0204 units. CPC slide posted on
Okay, sir.
23rd December, 23rd September. In that you have all the units
Okay,
of
sir.
pressure. Pressure, temperature, 2 slides are there on that. So,
Okay, sir.
so this is today will be the last tutorial. That is 10th tutorial activities. So your the 10th activity is over. Next semester for other courses we'll have something different. In case you have something in your mind which you are not still mentioned during the class committee meeting, you can mention it personally to faculty or to me. So I have already planned something for the next courses which is different than this time what we did. This is the core course, it's different calculation and a lot of new things are there. Next time will be a little bit different. And I want to do a lot of hands-on, but well, you have to come here. So that part I'm waiting. Let's see next semester. So typically heat transfer, we go to lab and do something so you can get better idea. In CPC also same thing, like concentration, many of you are not got it because you are not done a simple prepare one normal 1 molar solution in lab, you will immediately get the idea that okay, this many gram, this much amount of water, you get 1 molar solution or 5% solution or 5%, 5 mole percent solution. What is the difference? That basic things are will repeat whenever you come back next time, next semester. During tutorial, we'll spend some time on this. Okay, any doubt here regarding this from beginning to this lecture? Anytime you can contact me, ask me, and practice. That's the only thing. Read solved examples, take unsolved, similar, look like similar, you do that, and come back to me with your, send me screenshot, I can help you out. Okay, so I don't have anything new to add right now, new topic. We'll start it in the tutorial. You have any question? Up to this we have done. Anyone? There are several other books available on this topic, but better right now for this course, refer this textbook and that Felder reference book, two enough. Later for specific, for example, you are doing material balance only on evaporator, so you will have some more information about it in that. And then, for example, only distillation column, you want to do energy balance and material balance. So you will have separate unit operation. Each unit operation will have some specific calculations. So they have given in some other books. You can refer them. And
Sir, about the Compre,
yeah,
I've asked you whether we can use Python.
I'm waiting for the instruction today. I got some email, but still other things. I have to wait for the email from the academic division. Once they confirm, then I can tell you that what to use, what not to use.
Okay, sir.
And it's after all, it's a closed book. And so whatever the data or information you need, I will give you. I mean, like table and other things which are required, it will be given. So you can use that. So like one physical, that property table I already given.
Like for CP
And
calculation, you put it in Python, you just need
yes,
the input and you get the output. It's like a calculator, but much more simplified.
yeah, I understand that. But I have to make sure that I have to follow the institute guidelines. So once they confirm that okay or not okay, so that I can confirm with you. And the final exam